we're taking a look at number 5 from the motion of charges in electric fields assignment. This is a really good question to do. It involves a lot of different stuff, and if you can understand this one, you can probably understand anything. At first, it seems really confusing because you've got multiple parallel plates, you've got multiple batteries, but once you get it sorted out, it's actually pretty simple, and it really drives home some of the concepts that we've been looking at. So let's take a close look at number 5 here. It says 4 parallel plates are connected in a vacuum as shown at the right. An electron with a mass of 9.11 times 10 to the minus 31 kilograms, essentially at rest, drifts into the hole in plate X and is accelerated to the right. Assuming its vertical motion is negligible, it passes through hole W, goes through hole Y, and then continues to move, continues moving toward plate Z. And then we got to figure out a whole bunch of stuff, including its velocity here, and how far it is from plate Z when it stops. Okay, let's see if we can do this now. Okay. Now again, you first look at this and it looks super complicated because you've got 1, 2, 3 pairs of parallel plates. You've got 2 batteries. You've got a pair of parallel plates that aren't even connected by a battery. They're connected by just a wire, just a conductor. So at first glance, it seems super confusing. Like you just want to do that kind of thing. But we'll persevere and see what we can come up with. Tell you what, for starters, let's get rid of this wire. I have no idea what it's like to put a conductor in between 2 parallel plates, so I'm going to get rid of it for now, and I'm going to see what this situation looks like. Okay, take a close look at this situation. This is manageable, right? 2 parallel plates, they're connected by a 300-volt battery. Okay. This is the positive terminal of the battery, so this plate is going to be positive. This is the negative terminal of the battery, so this plate is going to be negative. Now remember, the potential difference between the plates is the same as the potential difference across the battery, 300 volts. Remember, a potential difference just represents a charge imbalance. Let's say, just for the sake of argument, that a potential difference of 300 volts means that we have 3 positive charges over here and 3 negative charges over here. It's not the most scientifically rigorous thing in the world, but that's okay. It gets the idea across. All right, so 300 volts of potential difference means 3 positives over here and 3 negatives over here. You could say that the charge imbalance here is 6 because, let's face it, the difference between positive 3 and negative 3 is 6. Okay, so we're going to remember that a potential difference of 300 volts means we have a charge imbalance of 6. Okay, so let's take a look at our other pair of parallel plates, the ones with the 500-volt battery between them. Now remember, this is the positive terminal of the battery, so this will be the positive plate. This is the negative terminal of the battery, so this will be the negative plate. Now, 300 volts of potential difference meant a charge imbalance of 6. So 500 volts of potential difference, well, a little bit of arithmetic tells you that the charge imbalance over here is going to be 10. Okay, so that means, well, again, over here, 300 volts, I had negative 3 and positive 3. Over here, 500 volts, I'm going to have negative 5. Whoops, they go on this side. And positive 5. Okay. And yeah, take a look. The difference between positive 5 and negative 5 is 10. There's my charge imbalance of 10. Okay, so if all we had was this, there's what it would look, piece of cake, right? But remember that someone comes along and just to muddle us up, or to try and muddle us up, they throw in a conductor like that. They run a wire between these two parallel plates. Essentially, they've touched these two plates. Well, if you touch two charged objects, they share the charges equally. Okay, we've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8 charges. Okay, so they're going to share them equally. So they're going to wind up with 4 charges each. The electrons flow between the conductors, so you wind up with 4 lonely positives here and 4 lonely positives here. Okay, makes sense? The conductor comes along, these two plates share their charge equally, and instead of having 5 and 3, well, now we've got 4 and 4. Okay, now what's happening over here? Remember, you still have 300 volts of potential difference between these two plates. That means you still got to have a charge imbalance of 6 between these two plates. That means if you've got positive 4 here, well, over here, you're only going to have negative 2, right? The difference between positive 4 and negative 2 is 6. Same kind of thing is going to happen over here. These things are going to adjust. 500 volts means you need a charge imbalance of 10. If you've got 4 positives here, that means you're going to have, the electrons are going to flow through the battery, and they're going to adjust so that you have positive 4 here and negative 6 here. Again, the difference between positive 4 and negative 6 is 10. So, perfect. So, there's how the final product is looking. A 300 volt battery here. Okay. Notice, nice charge imbalance in place across these two. 500 volt battery here. Again, nice charge imbalance in place across these two. A conductor in between these two. No charge imbalance here, right? Positive 4, 0 charge imbalance between these two plates here. All right, now we are ready to actually do the question. Now, once you've got this all figured out, doing the question is pretty easy. Okay. So A says we got to find the velocity with which the electron passes through hole W. So the electron starts with no velocity here. What's its velocity going to be over here? Well, first of all, convince yourself that as this electron goes from here to here, these negatives are going to be pushing it, these positives, they're going to be pulling it, and the electron is going to be speeding up, speeding up, speeding up. Just how fast is it going here? Okay. Well, how about this? Between here and here, the electron, its kinetic energy is increasing. And the work we do on it, is going to equal its increase in kinetic energy. Right? You remember that from the last unit. W is equal to delta KE. Work is equal to change in kinetic energy. In this case, the work is equal to the increase in kinetic energy. Okay, so the work, okay, well, that's going to be the charge times the potential difference you move it through, QV. The increase in kinetic energy, well, it's got no kinetic energy here, so however much kinetic energy it winds up with over here, well, that's going to be its increase in kinetic energy, and that's going to be 1/2 mv squared. And we have to solve this equation for v, little v, so you solve this equation for little v, the 2 goes up to the other side, and you're going to get 2qv, big V. The m goes down to the other side, you're going to have an m down there, and we got to take the square root of both sides, okay, to get rid of the exponent there. So yeah, little v is going to be equal to the square root of 2 times the charge, okay, the square root of 2 times the charge. And remember, the potential difference we're going to use is going to be in Newton meters per coulomb, so our charge has to be in coulombs. We got an electron, so that's going to be 1.6 times 10 to the minus 19 coulombs. Times the potential difference, which is 300 volts. And then you divide by the mass, which is 9.11 times 10 to the minus 31. You grind that for your calculator, and I believe that you get, I got it written down here somewhere, there we go, 1 times, whoopsie, 1 times 10 to the 7th meters per second. Try it for yourself, make sure you get the same thing. That answer makes sense. Generally speaking, when you start accelerating electrons through potential differences, electrons, they have such a small mass that they really hit some tremendous velocities. So most of the time, the numbers that you're going to get for something like this are going to be pretty big. So that answer makes sense. 1 times 10 to the 7th meters per second. Okay, that is A done. And then the next one is super easy. Okay, remember the velocity at W, we just figured that out. 1 times 10 to the 7th meters per second. Okay, now for B, we got to figure out this velocity. Okay, remember, there's no charge imbalance between here and here. Positive 4 here, positive 4 here. So there's no charge imbalance between here and here. So that means no potential difference between here and here. If this velocity is 1 times 10 to the 7th meters per second, any guesses as to what that velocity is? No calculation needed. Okay. I'll tell you what, let's see if we can figure it out. Okay. So again, the work done between here and here is going to be equal to the increase in kinetic energy between here and here. The work done between here and here is going to be, the work done between here and here is going to be QV. And remember, that's going to equal the increase in kinetic energy. But remember, there's no charge imbalance between here and here. This is positive 4, this is positive 4. No charge imbalance between here and here. That means the potential difference between these 2 points, the potential difference is 0. So your increase in kinetic energy is equal to, doesn't matter what the charge is, your increase in kinetic energy is equal to 0. So we know that, therefore, Vy is going to equal the same as Vw. There's no potential difference between here and here. That means basically there's no work done on the charge between here and here. That means the kinetic energy stays the same. However fast it was going here, well, that's how fast it's going over here at hole Y. So Vy is, what do we got? 1 times 10 to the 7th meters per second as well. Okay, now we're on C, the distance from plate Z of the point where the electron momentarily stops. Okay, so we're on C now. And first of of all, convince yourself that once the electron gets into this space, it is indeed slowing down. As it's going from Y to Z, well, these positives are pulling it backwards, these negatives are pushing it backwards, it is indeed slowing down, and eventually it's going to stop. But what we got to figure out is this distance. Of course, initially it's probably easier just to figure out this distance, and then this one's a piece of cake. We can do that later. First of all, how much distance does it take to stop? How about this? Remember, it took 300 volts of potential difference to accelerate this electron from 0 to this velocity. So how many volts of potential difference do you think it's going to take to decelerate that electron from that same velocity down to 0? 300 volts to get it from 0 to 1 times 10 to the 7th meters per second. How many volts to get it from 1 times 10 to the 7th meters per second down to 0? Well, if it takes 300 volts to speed it up, it's going to take 300 volts to slow it down. So there's 300 volts, not 500, right? There's 500 between here and here. It takes 300 volts of potential difference to slow it down between here and here. So what's this distance going to be? Well, we can just use ratios to figure that out, right? We can say the little distance, d, is to the big distance, 4, as the little voltage, 300, is to the big distance, or pardon me, the big voltage, 500. There we go. The little distance is to the big distance as the little voltage is to the big voltage. And then it's just a little bit of algebra, right? The 4 goes over the other side and goes upstairs, and when you do this algebra, you're going to get 0.6 times 4, you're going to get 2.4 centimeters. So this distance is 2.4 centimeters. So the distance we're interested in, well, that's going to be 4, take away 2.4, 4, take away 2.4, that distance is going to be 1.6 centimeters. Okay, and yeah, that answer kind of makes sense. Like 300 volts is a little more than halfway to 500 volts, so this distance should be a little more than halfway across 4 centimeters. This distance should be a little less than halfway across 4 centimeters, and it is. So things seem to make sense. Okay, last bit of the question. Now we're going to do D. And D says the velocity with which it arrives back at plate X. So think about what's happening to this electron. Okay? It speeds up, moves at a constant velocity, slows down, stops. Now when it stops, these negatives are still pushing it that way. These positives are still pulling it that way. So it's going to be stopped for about that long, and then it's going to start moving in this direction. It's going to speed up, constant velocity, and in here, well, it's going to start slowing down, right? These negatives are opposing its motion. These positives, they're pulling back on it. They're also opposing its motion. So how fast is the electron moving when it gets back to here? And it's actually pretty simple, because whatever happened as it moved out, well, the same thing is going to happen in reverse. Okay? It's speeding up through 300 volts of potential difference, so it's going to have that velocity in that direction. Between here and here, there's no potential difference, so when it gets to here, it's going to have that same velocity, except in that direction. And here, instead of speeding up through 300 volts of potential difference, well, now it's slowing down through 300 volts of potential difference, and it's going to arrive back here with 0 velocity. It's basically going to come to a nice, calm stop when it gets back here. So, answer for D. velocity 0. Okay? And if you can follow everything that we talked about in this question, you're in good shape because it encompasses pretty much all there is to know about how charges move in electric fields. And it also encompasses a lot about how a potential difference is just a charge imbalance. Okay, bye for now. Boy.